Welcome to Magic of Primes, a special series inside our mathematics playlist. Prime numbers looks very simple, right? But they hold the secret that powers puzzles, coding interviews, and even internet security. In this series, we will explore the beauty of primes, from checking if a number is prime to advanced tricks like prime factorization and sieve algorithms. So, if you're ready to see how much magic lies in these tiny numbers, let's jump into our episode 1, Checking Prime Numbers. Welcome to our very first episode of Magic of Primes. In this episode, we will be concentrating on checking prime numbers. We're going to see 4 different techniques, 4 different approaches in checking whether a given number is a prime or not. And this episode will be concentrating on the very first approach, a very simple approach. And before getting into the approach, let's first understand what is meant by a prime number. Let's take, for example, generally we will take n. N will be called as a prime number if and only if it has only 2 factors and one of the factor is 1 and another factor is going to be the own number itself, which is n. Apart from this, 1 and n, starting from 2 up to n minus 1, we should not be finding any factor between 2 to n minus 1. None of the numbers between 2 to n minus 1 should be dividing the input number n equally. Because for every number, 1 is a factor. For every number, own number is also a factor. And what is the difference? The difference is that between 2 to n minus 1, there is no factor for a prime number. And that's what we are going to check exactly in our approach 1. So let's say, for example, if I take n is equal to 7, let's take all values right from 2 to n minus 1. That is 2, 3, 4, 5, and 6. Now check whether 2 is a factor of 7. No, 2 is not a factor. 3 is also not a factor. 4 is not a factor. 5 is not a factor. And 6 is also not a factor. When there is no factor between 2 to n minus 1, then you can claim this number to be a prime number. But what about if the input is 9? Let's pick all the values 2, 3, 4, 5, 6, 7 and 8. Is it 2 is a factor of 9? No. Is it 3 is a factor of 9? Yes. When we find the very first factor, we can stop there and we can say that this cannot be a prime number. This is not a prime. This is not a prime. So the basic idea is, if a number n is provided, take all the values right from 2 to n minus 1 and check if there exists any factor between that 2 to n minus 1 for n. If there exists a minimum of 1 factor, stop and claim that it is not a prime number. But if you do not find any factor, then you claim n to be a prime number. And the concept is as simple as that. Let's look into the implementation of approach 1. So to start with, from the main function, let's start declaring a variable to receive input. So let's take long num. I'm using long because we're going to deal with bigger numbers. So this program will also work for bigger values also. And to receive input, we will use cin. So cin double greater than num. Now, after receiving input, let's write a function with return type boolean, and the name of the function is going to be is prime, and parameter we are going to place long num. So if anybody calls this function and passes an integer value, this function will check whether that number is a prime or not. If it's a prime, this function will return true. If not, it will return false. That is going to be the purpose of this function. So going inside, what does our approach 1 says? Our approach 1 says that we have to pick all the values right from 2 to number minus 1 and we have to look for factor. So let's pick all the values right from 2 to num minus 1 and let's go with for long I equal to 2 and I less than or equal to num minus 1 and I plus plus. So using for loop we have picked all values right from 2 to num minus 1. One clarity is that why I am taking I as long, because I is going up to num minus 1 where num is a long. Num is a long data type. So when num is a long data type, I which is going to get up to num should also be long. So that's the reason why I have taken I as long. Now coming inside the loop, we have to check whether we are picking a lot of i's, right? We are picking a set of I. What I is going to hold? I is going to hold all the values right from 2 to num minus 1. So we have to check any of that number is dividing the input number equally. So what is the input number? Input number is num. And we are going to check whether that num modulus any of our I is equal to 0. So if any I is dividing num equally and producing 0 as the remainder, then we have to say that I is a factor. And if this condition satisfies, then I is a factor. So when we find one factor between 2 to num minus 1, we can stop there and we will simply return true. Sorry, we will simply return false, indicating that it is not a prime number. But hope we all knows that when a return statement is executed, the complete function is abruptly stopped. Now, let's carefully listen. Let me come to 10th line. We will reach 10th line only if the return statement in 8th line is not at all executed for one time. When that return statement will not be executed, if the condition num modulus I equal to 0 is not at all satisfied for one time. If it is not at all satisfied for one time, which means that none of the I is a factor. What is I? I is value between 2 to num minus 1. So which means if that condition num modulus I equal to 0 is not at all satisfied for one time, which means that values from 2 to num minus 1, no value is dividing the input number equally, which means that none of the number between 2 to num minus 1 is a factor of the input number. When none of the number between 2 to num minus 1 is the factor of the input number, we can claim that to be a prime number. So reaching 10th line indirectly says that there is no factor between 2 to num minus 1. And if we reach 10th line, we can directly say that the number is definitely a prime number. So we will have to return true, indicating the same. Now let's come to main function. After receiving the input, now we will just check if is underscore prime of num. So when we call is prime and we pass num as the input value as the parameter, the function has to either return true or false. If that input value is a prime number, it will return true, or otherwise it will return false. So if that function is returning true, then we will just simply print cout prime. But suppose if that function returns false, then else we will go with cout not a prime. That's it. So now we can but one more condition we are missing, which is, what is the smallest prime number? The smallest prime number is 2. Which means this function will be working if the input is 2 or greater than 2. But if the value is 1 or if the value is negative, then this might not be working because we start our checking from 2. So first condition that we have to add here is, suppose if the input number is less than 2, 2 is the smallest prime number, and if the input is less than 2, no need of any checking. We can directly return false, indicating that it is not a prime number. So that's one condition we need to add, and I think now we can go ahead with the execution. And first I'll just compile this G++-O. So the compilation is perfect, no syntactical error. Now we will go with executing it, and now I'll go with the very first input 1. which is not a prime exactly. 2 is a prime. 3 is again a prime. 4 is not a prime. 5 is a prime. 6 is not a prime. 7 is a prime. 8 is not a prime. Then 9 is not a prime. Then 10 is not a prime. 11 is a prime. 12 is not a prime. 13 is a prime, and this goes on, and this works perfectly fine. But this is not a very efficient way of checking whether the number is prime or not. We have 3 more other optimized way of checking prime number, which we will see in our next episode. Thank you.